Hey there, physics students. So we are still working on being able to describe the relationship between displacement, velocity, acceleration, and time. And today, to that end, I have a little lab activity for us to do where we're going to take some data from the lab and we're going to make a velocity versus time graph with that data. So in the lab here, I call it velocity versus time graphs. Okay, now picture and imagine for a minute. Okay, think about this. This is kind of help you get the concept and the idea of what we're going to do in the lab. Okay, imagine you're driving a car, and your car is leaking oil, like it's just dripping oil. And so every regular time interval, every so often, say maybe once a second, it drips an oil drip. Okay, now you're dripping your oil drips as you're driving along, and you take off from a stop sign. Okay, could I look at the oil drips and understand the motion of your car? And the answer is yes, because all of the data about the motion of your car is preserved in those oil drips. Okay, let me show you what we got in the lab and what we're going to work with. The little setup I got here, all right? I got a little car, and this guy can move about, right? And he's tied to a string, and you see on the other end of that string, there's a weight. And when I hang the weight off of this pulley here and I drop it, that's going to pull the car along the table. And then the car will go racing along the table. But it won't just go racing along the table, it'll be accelerating along the table. And that's important because our velocity is going to change over time, and that's kind of the point of making this graph. It's a velocity versus time graph. We want to see a velocity that's going to change because that's the interesting part. You'll see here this other thing. It says on there that this is called a spark timer. This is actually not a spark timer. This is kind of like a spark timer. I've worked with an actual spark timer, and it's like really cool. It's got this high voltage thing. It makes this really high voltage, and every so often it will make a big old spark, and it will put a hole in the paper, so that as your paper gets dragged along through there, it will make a hole in the paper, and kind of like your oil dripping out of your car taken off from the stop sign, right? But this isn't a real spark timer, even though it says spark timer. You see it's got a little piece of carbon paper in there, so that what it's going to do is it's just going to make a dot on the paper rather than making a big old electric zap and putting a hole in the paper. So it'll be fun there. Okay, so this is the setup that we've got. Okay, so I'll start the car going. We'll have this thing making dots, and then in the end I'm going to have a piece of paper, a paper trail if you will, that I'll have a whole bunch of dots on there. And the thing about this spark timer, or this pseudo spark timer, that I know is it makes a dot every 1/60th of a second. So I'll be able to look at my dots, and I know exactly how much time is between them, and I can measure with a ruler the distance between them. So let's go ahead and check that out. Okay, let's check out what's going to happen here. Okay, so now I have the tape here that ran through that kind of pseudo spark timer thing, and I'm going to show you. Can you see right here at the beginning? You see the dots? I've actually gone through on this, and I have made the dots a little bit darker with my pen. If I hadn't have done that, you wouldn't be able to see them. But you can see here the dots at the beginning. They are all close together. You can see occasionally there's a spot like right here where there's one that's skipped, like maybe the dot didn't quite get punched onto the paper very well. If we had an actual spark timer, I don't think that would happen. But you can see the dots close together, and as we go along the tape, they get further and further apart, which is what you would expect to see with an object that's accelerating, right? It's going faster and faster and faster, then the dots should get further and further apart. So now what we're going to do is I'm going to get a ruler, and I'm going to measure the distance between the dots. And then, of course, there's some where I'm going to kind of estimate the ones that got skipped, right? I'm going to kind of estimate where they are. And we're going to make a big old table. And I know each one of these dots is 1/60th of a second apart. So the first dot is 0, the second dot is 1/60th of a second, the third dot would be 2/60th of a second. The third dot, or the fourth dot, would be 3/60th of a second, and so forth. I'm going to measure the distance between them. I'm going to record the corresponding time, and I'm going to end up with a big old table. Now, I'm not actually going to write this out on paper. I'm just going to open up graphical analysis. I'm going to put all these numbers in there. So the next scene in my video, you should see graphical analysis on the screen. Okay, so. All right, so I have taken my tape with all the dots on it, and I have measured the distance to each one of those dots. So the very first, how far is each dot from the very first one? Right? So the very first one is at 0, and then I measured the distance from there to each subsequent dot. And I have created for myself a nice big data table here, where you can see under the position heading, I have the distance of each corresponding dot, how far it is from the first one. And you notice the total distance, the very last dot, was only about 1.4 meters from the first one. So while I was taking data, my car only traveled about 1.4 meters. And in my other column here, under time, I put how much time for each dot, right? So the very first dot was made at 0 seconds. And then the second dot was made a 60th of a second later. And so a 60th of a second is about 0.017, right? And then each subsequent dot, this one was made 2/60th of a second later, this one is 3/60th, and so forth. And you can see my very last one is 0.850 seconds. So my entire experiment lasted less than a second, and now we're just analyzing the data, right? You see all of these data points I took, 52 data points in less than a second. Pretty neat, huh? Okay, and you can see on my graph, they don't line up straight, and I don't expect them to line up straight. I have an object that was accelerating, and here in my position versus time graph, I wouldn't expect them to line up straight. I would expect them to be more quadratic, and if you look at this graph, it does indeed appear to be quadratic. You can see some spaces on the graph where it kind of looks like it jumped a little bit. Like you can see notably right here, looks like there's a little jump or a little break. Right here, it looks like there's a little jump or a little break. Right? These correspond exactly to those points on my tape where there was a dot that just got skipped. Right? So that's what those are. These little breaks that you might kind of notice. They're just places where the spark timer didn't adequately put a dot. So now, if we take a look at it, I can apply a little curve fit. I can say this looks quadratic to me. So I'm going to pick quadratic, and you can kind of see, look, it lines up pretty nicely with the quadratic model. So this is quadratic. Now, if you look at your lab handout, or it's probably a digital copy for you, the next thing it wants you to do is it says linearize the graph. Okay, and what that means is we're going to make it straight. Okay, now how are we going to do that? Is we're going to add a new column. What we're going to do is we are going to take what's on our x-axis, which is the time, and depending on what the graph looks like, this one looks quadratic. So since it looks quadratic, what I'm going to do is I'm going to take that column, and I'm going to take every single one of these numbers, and I'm going to square it. Now I could do that by hand with a calculator, but this program has a nice little calculated column option, so I don't have to sit here and 52 times square 52 different numbers. What I'm going to do, this is going to be time squared, and it'll be measured in seconds squared. Okay, and then if you look at your lab handout, it says insert an expression. We want the type a times x to the b. A should be 1, x should be the time, and then b, we want to make that 2 because we want to square it. And you can see that gives me this nice calculated column right here. And if I go ahead and change what's on my x-axis to this new one, instead of having time, I'm going to make it time squared. And look at that. Now it kind of looks like a nice fairly straight line. It kind of curves off a little bit. That's okay. Looks like a nice fairly straight line. So let's do a curve fit, and this time we'll make it a linear curve fit. A linear fit. To see if it fits fairly well. Not the best fit, but it fits fairly well. See, it kind of drops off at the end there. I think that's probably the result of friction working on the car. If there wasn't friction working on the car, I'd expect to see that just go nice and perfectly straight. Okay, and now in your lab handout, what you want to do is you want to find the slope of this line, which is easy because it's in the box right here. You see m? This is 2.019 is the slope of your line. And since all the numbers I measured had 3 significant figures, I would only trust that to 3 significant figures. I would call that 2.02. And then, of course, what's going to be the significance of this line? Is it should be the acceleration of the car. So the car should have accelerated at 2.02 meters per second squared. And let's see. Wants us to find the equation of the line, which is fairly simple because it gives us everything we need to know right here in the box. So the equation should look like y equals mx plus b, just like you learned in your algebra class, right? Y is what's on the y-axis. What do we put on the y-axis? We put the position. So that's delta x, right? So instead of y, put delta x. And the slope is that number right here we just talked about, 2.02. X is what's on the x-axis. So what's down here on the x-axis is time squared. So I would put t squared. And then b is your y-intercept, which should be 0. So here we'll put delta x equals 2.02 t squared. And that's about it there. So pretty neat stuff. Hopefully that gets us a step closer to understanding the relationships between acceleration and time and position and velocity. And until next time.